Okay, I think we're online. Hello everyone, my name is Sergey Yastribov. I'm a community lead from Facebook Developer Circle Moscow, and I welcome you today at the second day of Deep Learning Online Meetup. If you didn't see previous presentation, which happened tomorrow, where Shri Sharma talked about self-driving cars, you can check our YouTube channel and basically watch it in record. If during the presentation or afterward you will have some thoughts or questions related to today's topic, you can write in a live chat or in the comments. Just keep in mind that live chat won't be available after live section is over. So if you have some complicated question or you want to continue discussion further, use comments. And now let me introduce our today's speaker, Sergio Garrido, who will talk about deep generative models for tabular data. Welcome, Sergio. You can start sharing your screen and start your presentation.
Thank you very much. All right. Can you see my screen now?
Yeah.
Okay, great. First of all, I would like to thank Sergey for the invitation. I am very honored to be presenting to all of you in here. Okay, let's get to the matter. So today I'm going to present deep generative models for tabular data. This is joint work that I do with Stanislav Borisov, Yeparich, and Francisco Pereira. I'm a PhD student at the Machine Learning for Smart Mobility Group in the Technical University of Denmark. So let's begin with the problem. So we have a potentially small survey of high-dimensional individuals, and we want to generate individuals to resemble the whole population. So to give an example, let's say that a surveyor comes to your house and asks you, how old are you, how many cars do you have, whether you have a bike or not, and so on. And this is then this is tabulated into an Excel file, and maybe the surveyor doesn't go to every single house in Denmark, in my case, but the surveyor goes into a representative sample in Denmark. Now, the thing is that we need this data, and we need actually the whole population in order to run some models, let's say on transport demand or on healthcare policy and so on. So basically, this is what I just said. These generated agents are going to be the input for what are called agent-based models. And having the whole population is the actual input of interest, and not only the survey. And another important motivation to do this is we, for example, would like to release sensitive data. So I just mentioned some medical and healthcare data. So in many occasions, if not all of the occasions, these are data that people don't want to be released. People maybe they don't want to know that, or maybe they don't want other people to know that they have a certain disease, or for example, for insurance companies, is not always good if they have all this data, all this sensitive data or healthcare data from other people. So the proposed solution, or what I'm going to present in here, is to use a family of models which lie in the intersection between neural networks and Bayesian inference to generate these very high dimensional agents. So I won't go into the detail of all this research, but what I want to convey with this slide is basically this is a popular area of research. For those of you that know the major conferences in machine learning, you can see that the first one and the second one is from generative, the second one is on iClear, and so on. But the most important thing is that this is an area of research that has been going for a long time. Not particularly with the application of neural networks, but that of generating population data out of survey data. Particularly, these ones below that are in red are from the lab I work in. And even more particularly is that I'm going to present this paper that was accepted to be published in Transportation Research Part C. Of course, this wasn't an exhaustive list of all the research that is out there. There's a lot of research, and most of all with these deep generative models is nowadays exploding. And even kind of to convey the message even a bit further is the fact that there is a challenge for neurips in this year, which is called the Hide and Seek Privacy Challenge. I'm doing a little bit of advertising, although this is nothing related to me, where you need to generate this population, or you need to generate some data with some privacy guarantees. All right, so before I go into the detail of what's going on and the models and so on, the key takeaway, what I want you to take home is that we can actually synthesize, or we can create high dimensional data using deep generative models. However, of course, as always, there are going to be some caveats. So the aim of this presentation is going to be more or less a high level. I won't go into all the mathematical detail. Of course, I just gave you the pointers, and if you want to go into the detail, you can always take the presentation or the video and just check out the details in the papers. I'm going to explain deep generative models in a very concise ways. The idea is that you have neural networks, you have also probabilistic reasoning or Bayesian inference on the one hand, and the idea is to have latent variable and use neural networks in order to make these latent variables, or draws from these latent variables to convert it into very expensive data. These are not the only type of deep generative models. This is just a subset, which are latent variable deep generative models. There are, for instance, other ones that are autoregressive, and those are not. Those don't need to have a specific latent variable definition and so on. In these latent variable deep generative models, we can find very popular models such as the VAE or the generative adversarial networks or the normalizing flows, which I'm going to explain in what follows. So these are some of the deep generative models, latent deep generative models. I'm going to explain briefly the three of them, and then I'm going to go into more detail of the VAE particularly, which is this one on the left, and the generative adversarial networks, which are these on upper right. So basically, the VAE is a relatively simple model. We have two networks. One network is called the inference network, recognition network, or encoder. And what this network does is it takes the real data, your tabular data that defines you, or image data. It doesn't have to be tabular data. Then it will infer some posterior distribution of that data. So it's going to infer, in most cases, the mean and the variance of a normal distribution. And then with samples from that distribution that we just inferred with the real data, we're going to have a decoder or a generative network, which converts those samples back into the real data. And so basically this type of model, it's trained so that the input data resembles very much the output data, but there is also a constraint on the posterior distribution, which is this set that we inferred, to be close to a prior distribution. This is VAE in a nutshell. This was proposed more or less jointly by Kinman Welling and by Danilo Resende and Shakir Mohammed. The second famous deep generative model was proposed by Goodfellow and co-authors in 2014. And actually, it has also two networks. So the kind of invert in a certain way. First, we're going to start from some latent variable. We're going to generate some samples from that latent variable, and we're going to transform them using a generative network so that hopefully, let's say, the output of that generative network resembles very much your data. Now, how do we make sure that these samples resemble the real data? Well, then you use another neural network, which is going to take either real data or fake data, so data from your generated neural network, and it's going to have a certain probability of whether your data is real or not. And so basically, this discriminator network, what is called, or a critic network, is going to give feedback to the generative network so that the generative network is going to change parameters, is going to tweak itself, let's say, to make it resemble the real data, so that the discriminator can't discriminate basically between real and fake data. Finally, this is an recently exciting, let's say, area of research of deep generative models, particularly which are called normalizing flows, and they were proposed a long time ago, actually, by Tabak and Turner, but even in papers before 2013. and they were introduced more into the machine learning literature by Daniel Rosén and Shakir Mohammed, the same from the deep latent generative models. And the idea is also very similar. You start from a very basic distribution, in this case it would be Gaussian, and then you transform it somehow into more complex distributions. The idea of these transformations, which I call F in here, is that they are invertible transformations. And with these invertible transformations, what is guaranteed is that you can either come from the data into a basic distribution, and then you can evaluate the likelihood because you know this distribution and you can evaluate the likelihood of this distribution. But on the other hand, you can also take some samples from this distribution, transform it, and have some samples hopefully resembling that of your data. So this is deep generative models in a nutshell. I hope that you kind of understand the idea. The main idea in here is basically we have some base distribution, and then we transform it somehow so that it resembles our data. Now let's look with a bit more of detail the VAE and the GANs in the context of tabular data. Oh, and before that, kind of the magic thing about these deep generative models is that we can take all the advances from the neural networks to create probabilistic models and to create richer probabilistic models. So for instance, you can think about richer architectures, ResNets and convolutional neural networks and so on. And you can also think about optimization procedures, RMS prop and so on. But of course, everything that is in the literature of neural networks can be applied into these deep generative models, or virtually everything, let's say. And on the other hand, we can use this, let's say, expressivity somehow of the framework of the probabilistic models to give a bit of more of structure into our neural networks, and in a certain way, a bit more of interpretation. So let's see a little bit the VAE with a bit more detail, kind of in the categorical data setting. So basically, the input layer is going to be mostly one-hot encoded variables. So as I said before, the gender of a person, the age of a person, which is not going to be categorical, in fact, whether the person has a license or not. You're going to run this input layer through some transformations that are these neural networks. We're going to learn some form of representation, in fact, that is going to be in the latent space. So then you're going to extract some parameters of a distribution. Very normally is used normal isotropic distribution, so it's just diagonal Gaussian. But you can use, in fact, many different distributions as long as they can be differentiable, and some conditions that are basically technicalities. Then you take some samples from this distribution that you just learned from before, and you transform those samples again with some form of representation, so that the output layer resembles as much as possible your input layer. So we would like basically to the rightmost layer to be as close as possible to this input layer, so that also the latent space has some certain closeness to some prior distribution. Both of these neural networks are trained jointly, and let's say at generation time. So what we're interested, remember, is to create the population based on a representative survey. At generation time, we're going to forget about this encoder or this inference network, and we're going to keep the generator network so that we sample from the prior distribution, just a standard Gaussian. Then we're going to generate in a certain way novel agents or novel individuals. All right, so this is going to be one of the models we're going to use. Particularly, we use the variant of the VAs, a simple variant which is called the beta VAE, which just adds a form of just a multiplicative term in the divergence between this latent space and the prior that I just mentioned before. Now let's check the generative adversarial network. As I mentioned before, it's composed of two neural networks. One neural network is going to be the the generator. So you're going to start from, again, something similar to what I said before. You're going to start from a standard Gaussian distribution to standard diagonal Gaussian distribution. You're going to somehow, and the somehow is using a neural network, transform the distribution so that it resembles the data that you want. And these fake samples are going to be the input into the discriminator or a second neural network. And this neural network is going to tell, okay, what is the probability that this particular data point is real or fake, right? And of course, at the beginning, this is going to be very noisy. So this neural networking here is going to generate basically noise. But as the discriminator gives more feedback to the generator, then the generator gets a little bit better by tweaking itself. And there comes like a two-player game, what it's called. So on the one hand, the discriminator is getting better, so the GAN is better at discriminator what the generator is doing. And on the other hand, when it receives the feedback from the discriminator, the generator gets better at generating samples. The ideal point or the equilibrium point is a point where the discriminator can't discriminate between fake samples and real samples. Again, in the particular work, I didn't use the basic generative adversarial networks, but I used the Wasserstein generative adversarial networks, which somehow have become the let's say the most widely used. Of course, there's a whole slew of variational autoencoders and generative adversarial networks, but we chose those. They did the job properly. Okay, so now let's go a little bit into the data. We use data from the Danish travel survey. These are approximately 178,000 people. This is a representative sample of the whole population, and this is what is called a repeated cross-section. So that's basically you don't observe the same person every year, but you just do a representative cross-section, so a representative picture of a population every year. This is a data set that is still going, and it's a very rich data set. Particularly, I didn't use that many data points because I wanted to test the robustness of these models to low data settings, which is basically the whole idea of the model. So I used only 7,000 samples for training and 7,000 samples for testing. And this data set contains individual characteristics and some of the travel behavior of people. This is not an open data set, but you can ask or you can request for access. Okay, so yeah, I'm sorry. Yeah, so how to evaluate these models? So in the computer vision and natural language processing, there are a lot of common metrics, and these metrics are based on log likelihood, on Fréchet distance, inception distance. There are a lot of there has been a lot of research on how to evaluate these models, but the truth is that these models have some of these metrics fail at some times. And there is a very nice paper by Lucas Face, if I remember properly, that kind of explains in detail and even with some basic mathematical examples why the log likelihood might not be a good metric to evaluate models, why the Fréchet distance is not so good, and so on. So basically, what Face and co-authors argue is that the best thing to do when you have deep generative models is to create your metric based on your case. So based on the particular task that you have. So let's say classically in transport, the way to evaluate population synthesis is, you take a couple of variables. So in this case, you take municipality of origin, municipality of destination, and you check how well does the predicted frequency counts match the true count. So again, you generate, let's say, 100,000 individuals, then you do the frequency counts of each municipality of origin and each municipality of destination. So it's a combinatorics, right? And then with these frequency counts, you check, okay, whether the test data matches the generated data. So in this case, we can see, of course, the classic, what everyone would say, okay, the WGAN performs way better than the VAE and so on. And then you have this R squared and square root mean squared and correlation coefficient and so on. So you can, of course, scale up the number of combinations, particularly, so to give you a bit of an explanation of the order of magnitude that we're talking here. Municipality of origin is 100 different values, can take 100 different categories. Municipality of destination can take 100 different categories. Income, we separated into seven brackets, and labor sector 37 brackets. So you have to multiply 100, 100, 7, 37, and then you get all the possible combinations. So as you might see, these can explode really quickly. And you can see that in here, right? Because we're already in this type of combination, we're already trying to predict probabilities of 0.001% of the data. This is very, very, very sparse data. Now, when I was doing this classical way of evaluating models, I wasn't completely satisfied, because actually there can be some artifacts in the generated data that might make your model seem better than it is. And this is related a little bit with what I explained before. So some of these metrics might not be appropriate. And I thought, okay, so let's say, for example, something that you might be asking me is, okay, so what if you're just matching the distribution in here because you're just copying the agents that came in your survey data? And that's a possibility, right? If you overfit, you maybe some of you guys know the term, and most of you probably know the term overfitting. If you're overfitting your neural network to your survey data, then you're just going to generate the original agents and you didn't learn anything, right? You want to learn the underlying distribution. Okay, kind of based on having this in mind, I came up with this slightly different but strongly related idea, which is that of this sampling and structural zeros. Interestingly, I found later that this terminology of sampling and structural zeros has been also worked in the literature, and with similar meanings, but not exactly the same. So let me try to explain briefly what is this about. So the idea is that we have a universe of combinations. For certain variables, we have a universe of combinations. So let's say for municipality of origin, municipality of destination, we had 100 times 100 combinations. That's 10,000. However, if you think about it, let's think about the states, something that maybe people can relate to. People don't travel every day, let's say from Seattle to Miami in Florida. That'd be like corner to corner, right? So even though there exists a universe of combinations, actually there are combinations that do not arise in the population. And that would be people commuting every day from Seattle to Florida. So there is a subset of the universe of combinations, which we can call the combinations of the population or whatever. And at the same time, because you're sampling in a survey and you don't have access to all the people unless you're making a census, there are going to be the combinations of the survey are going to be a subset of the combination of the population. Of course, the combinations that arise in the survey, unless you have some mismatch, so some maybe errors in errors in measurement, then they shouldn't be overlapping with the universe of combination. The combinations of a survey should only arise in the combinations of a population. So then we can introduce two of these terms. One is that of the structural zero. So the structural zero is basically the combinations that arise in the universe of combinations of Seattle, Florida, but that actually can't exist in the population. And we can also introduce something that is called a sampling zero, which is basically those combinations that actually exist in the population, but because of the artifacts and the randomness of the survey, you don't get in your particular survey. So if you think about it, if you think from a perspective of policymaker, of a transport planner, you would want to get as close as possible as this big oval in here, and not just only, let's say, overfit to what you observe in the survey. Now, the problem is that maybe while you are trying to expand this through a neural network to the whole population, you might also get outside of it by getting some combinations that actually do not arise in the population. So basically, you want to get as many sampling zeros as you want with as low structural zeros as you want. So let's see, how does that look in here? Oh, okay. Oh, wait. There's something very important to say. So we have to zoom in a little bit in here, because of course I'm telling you that I have only the survey of population, so I don't have the full population. I don't have the census. So in order to actually make this evaluation valid, we would need to assume something further. So if we zoom a little bit on the survey that we have, what we need to do is, okay, this red circle is this red circle in here. What we need to assume is that our survey is going to be the population, that our training data is going to be the survey, let's say. And so basically what we're saying is that the test set, whatever is in the survey that is not in the training data, is going to be basically the sampling series. And we would like to see, okay, how well does the model, given this training data, match those values of the population of this artificial population, let's say, that we created in here. And if you think, okay, but that's not so good, because in any case you don't know what is being generated in the population and so on. So what you can think about is that, in fact, the structural zeros that you generate is a lower bound of the structural zeros in here. So let's say that a structural zero that you have some sampling zeros in the population. So these individuals in here, and then you assume this thing from the survey, then it means that if you generate something outside of your survey, it might be either a sampling zero or a structural zero. And so all the structural zeros that you generate from this generative model might be, it's just a lower bound on the actual structural zero of the whole population. This might be a little bit confusing, but maybe with some of the plots, this might be slightly clearer. All right, so I'm going to show you two types of results. One is of the combination of variables. So basically, again, I take a municipality of origin, municipality of destination, and we take like two dumb baselines. The two dumb baselines is sampling from the marginal distributions from your data, or sampling from fully random distribution. So what we can see is that the dumb baselines are very good at generating sampling zeros. So in fact, with a couple of thousand, maybe 150,000 samples generated, you already created all the sampling zeros, while the VAE and the Wasserstein-Gunn still haven't created. And in fact, even after 500,000 samples, they're not able to generate all the sampling zeros. But remember that there is a compromise between sampling zeros and structural zeros. So on the other hand, then if we check the structural zeros, we see that the VAE and the Wasserstein-Gunn are way better at not generating structural zeros. So in fact, the random and the marginal models, so the dumb models, create 100% of the structural zeros. So this is not very valuable. And actually, if you check both of these metrics by themselves, they're not very meaningful because of this compromise that I'm talking about. What you actually want is some form of ratio that takes this compromise into account. So what if you take basically structural zeros over sampling zeros? Then it's going to tell you what you want is this value to be very small, because you want the numerator to be very small and the denominator to be very high. And for different number of observations generated, we can see that the Wasserstein-Gunn is slightly better than the VAE and considerably better, let's say, than the random and marginal distribution. So this is 10,000 possible combinations. This is not such a big problem. We'd like to scale this up and see what happens in higher dimensional settings. So already with 2.5 million possible combinations, we can see that the VAE, it's way better at generating these sampling zeros, while the Wasserstein GAN is still close to the marginal random dump generator, and the purely random is very bad at generating sampling zeros. On the other hand, we can see the Wasserstein GAN is way better at generating structural zeros, and well, the VA is kind of in the middle, and of course the dump baselines are very bad. And again, we can see this in the ratio, which is actually the meaningful metric, and we can see that the VA and WGAN are way better than the dump baselines, but maybe you can't see that very exactly from the graph. But the Wasserstein GAN is also slightly better than the VA. This is maybe taking into account that both the previous one and actually all of these are going to be in the logarithmic scale. So there might be a big difference even if it doesn't look like it. And finally, kind of the same story with 140 million possible combinations. This is huge dimensional problem. And we can see that the VAE and WGAN are able to generate sampling zeros. So this is kind of an intelligent generator. And again, the WGAN is way better at not generating structural zeros. You can see the difference between the ratio here a bit more greatly. Now, the other set of results that I want to show you in here is, okay, what if we fix the number of samples we take? So in here, we're just generated a number of samples and we have a fixed number of combinations. And then we're just checking how many sampling zeros do you get and how many structural zeros do you get and the ratio. So now let's do kind of the inverse problem. What if we fix the number of samples, but we vary the dimensionality of the variables? So as we said before, you can have some lower dimensionality of the variables. So in the case of municipality of origin and destination, that was only 10,000. But you can go as high as 800 million, and if you add a couple more variables, then it explodes into even the billions. And then we can see with 200 samples, how many sampling zeros are you able to generate, or what percentage of the sampling zeros. So in this case, you can see, of course, that the percentage of sampling zeros that are generated by the VA and the GAN for all the dimensionality of the variables, of interesting combinations of variables, is way higher in percentage. Again, the structural zeros here maybe is not so clear, but again, this is in a logarithmic scale. The VGAN is considerably better in logarithmic scale, while the VA is slightly better than the other ones. But of course, this logarithmic scale, so this might not be telling. It's hard to see with the bare eye. And of course, a message that might be somehow logical from the story that I've been telling you is that as the dimensionality of the variables or the possible combination increases, then the number of sampling zeros that are generated are small, and it decreases. And of course, the ratio, which is the actual metric of interest, it's better for the VGAN and the VA. And in fact, as kind of a story, we didn't have any idea, or we didn't have any premeditated, how do you say, we didn't have any bias towards any model at the beginning of the VAE or the WGAN, but it proved to be that the VGAN is slightly better, or considerably better, at least for this task, as the VA. And for those of you that are interested in deep generative models, this is this is consistent with the literature, let's say, in image generation, where GANs are able to generate images with more fidelity, while the samples from the VA tend to be a bit more noisy, and WGAN. Okay, so kind of to recap first, we can use these latent deep generative models in order to generate or synthesize these agents. You can think of them in different ways. So you can think of them as a way to extend a survey into a whole population. You can think of them as, let's say, compressing your data set into some form of generator. And all these interpretations are valid, and actually they might aid some future research on the matter. Now, these models that I presented to you and these data that I presented to you are relatively basic. So there are some of the things that we would like to think about. And actually, this first point in here, which I'm going to mention, it has been treated in the literature quite a bit. Because so basically, how can we guarantee that the data that is released is actually safe data? So is it data that where you can't identify individuals within the data set? So even if you are generating them from random noise, there is a chance, as I mentioned before, that you're overfitting the data, and maybe you're going to release some particular agent. And this is something that we don't want if we're releasing the data. So this has been treated in some papers, particularly the Pategan and TimeGAN, and basically Michaelas van der Schaar, the creators of this competition that I mentioned before, are making effort on that. But some other interesting questions which I haven't seen so far is, okay, so how do we work with missing data? So I have checked the code from Michaelas van der Schaar, and for instance, they do median imputation into the missing data. And maybe you can also think about, just drop the values of the missing data, but can we come up with some clever idea of imputing missing data so that it doesn't, imply kind of these heuristic ways? The statistic literature on missing data is very, very vast, and maybe we can think about something here. And of course, kind of the logical thing to do is always to have richer models, richer architectures, and ways to optimize the architecture and so on. I think that's probably most of the history that I wanted to tell you. And I'm now open to questions, and I'm also going to check if there are some questions in the YouTube. Let me see.
Thank you for a great presentation. Actually, yes, we have some question in live chat. I think you talk about it just to check. Andres asking, using a relatively low number of train set with so many variables, how do you actually avoid overfitting? And is there a common problem for survey and generative survey actually to deal with overfitting? Because your survey has like 10 or, for example, 20 questions, and if you have small number of results, like few thousand, you can have overfitting. So can you please summarize and maybe talk about it a little bit more?
Yeah. So this is a great question. So as you might have realized from what I was presenting before, the dimensionality of this data and kind of the combinations that can arise in this data, it's huge. So you have millions and maybe billions of different combinations of agents. And of course, the idea would be to stay away from just overfitting to the data and generating those particular agents and so on. So there are different ways. So this is maybe where the neural network formalism can come in and help a little bit. So you can use, let's say, regularization techniques. You can use maybe dropout, L1, L2 regularization. And in some cases, it should be enough. Of course, you have to always check the validity of your estimates. And for instance, some exercise that I did that I didn't mention in here is checking, okay, how many agents of a created pool, let's say I generated 200,000 agents, how many of these agents are exactly the same as my survey agents? And if you do that check, what you should expect is actually them to not be, so that value to be 0. And when you have very, very high dimensional agents, kind of the probability that you will generate an exact agent is going to decrease considerably. So, for instance, you can check David Mackay's book. He has a bit of the explanation of why in very sparse spaces, the probability it's concentrated in very small spaces.
Okay, thank you. I don't see any other questions.
Yeah.
So maybe we're going to share some links for additional materials or maybe to your presentation in description or in comments later.
Yeah.
Maybe also people will think about some other questions and write them in the comments. So we're going to check them also later. Thank you again for your...
Yeah, I want to, maybe kind of to complement a little bit what you said, thank you, is that, of course, feel free to send me an email if you have any more ideas on this matter, or you would like to maybe collaborate, think something about this. This is, as I mentioned, some exciting area. I can share also papers if people just want some references. I can give some references, both on neural networks, on probabilistic models, and this particular tabular data generation thing.
Mm-hmm. We get some other question from live chat. Will these methods work from someone who changed their states? I mean, I think answers over the time. For example, if someone did survey in 1 year and then changed their answer in other year, will there be some problems?
That's a very interesting question. And this particular model is a pool of agents. So we're taking the 2006 agents to be the same as 2016, but you can come up with some richer models in which you kind of take into account the dynamics of the population. And I can even give you some reference now. So for instance, actually this time gun, the time gun from Mihaela van der Schaar lab, they do have a little bit of this time dynamics of how the population evolves, but this is for specifically for individuals and not for the whole the population as a whole. So maybe what you would want is a bit of a model that models the dynamics of the whole population. But yes, this is very interesting question, and I think there's a lot of things to do.
Okay, let me check. Yeah, so maybe if anyone else has any question in the future, please write them in the comment. We're going to check them later. Thank you, Sergio, again for your presentation and for your time. Next presentation will be in 2 days on Sunday at noon Moscow time, where Ruslan Martinov will talk about his experience of creating automation content recognition system for audio content. So don't forget to like this video if you find it interesting. If you have any question, again, write them in the comments. And you can share this video with your colleagues and friends who might be interested in today's topics. That's all for today. Have a nice time and see you all in 2 days. Bye.
Thank you very much. Bye-bye.